Hello there and welcome to this course on machine learning with R. My name is Valentine and I'll be your instructor. In this course, we are going to take the structure. So we are going to get started learning about the learning outcomes of the learning experience. After that, we'll talk about what those concepts, what those important concepts in relation to machine learning with R entail, why we would want to use R, as well as also get to learn about those concepts. And also when we apply those concepts when it comes to data analysis or machine learning projects, or just generally in a workplace. After that, we'll get into a practice session where we will put into practice those concepts that we will have learned now using the Python programming language. We'll provide explanations, code examples, and also provide you with challenges that will allow you to put into practice and acquire the skill that you'd require in order to create machine learning projects in R. Then towards the very end, we'll talk about the next steps. All right, so let's get started. By the end of today, we expected to have achieved these learning outcomes. We should be able to explain the significance of R in machine learning, emphasizing its libraries. We should be able to recognize examples of R-based machine learning tasks, such as regression, classification, and clustering. We should also be able to differentiate supervised, unsupervised, and reinforcement learning, highlighting their unique approaches. These are the different categories that pertain to machine learning. And lastly, we should be able to apply R's machine learning capabilities in real-world scenarios, using regression, classification, and clustering techniques to solve specific problems. You'll note, of course, we talk about machine learning in R, but we don't go extensively into other concepts that you might maybe have heard of, maybe something like dimensionality reduction, which is one of it's a type of an unsupervised learning task that one might want to perform. We also don't go into something like market basket analysis, which is also another type of an unsupervised learning technique. Our focus is to ensure that by the end of today's learning experience, you have a good understanding of what machine learning is. This workshop is majorly geared towards people who are new to machine learning when it comes to working with R. But at the same time, also new to machine learning. We would understand that maybe you might have come from a background where you have just been learning about R, but would want to see how you can use R to work on what are called machine learning problems. So our focus will be on that. You can think of this workshop as an entry point to machine learning. Other workshops or learning experiences that would come in after this workshop would most likely focus on one area of machine learning, whether that is on regression, on classification, on clustering, or even on advanced techniques such as ensemble learning. There's so many topics in relation to machine learning that you could go deeper into. However, this is just a quick introduction. Something else to note, we have ever delivered this course in the past, but if you probably never got an opportunity to be able to go through this particular course, then this course should help you come up to speed. But if you've ever gone through our machine learning with R task in the past, it's actually the same workshop. So you could always maybe consider focusing on another aspect of R, or you could always, by just simply looking at our other course offerings on our platform or on YouTube, or you could decide to, continue learning and recapping what you did cover in the past. All right, so let's get started with machine learning with R. So what is machine learning with R? So this is just the process of using the R programming language, which is a popular data science, data analytics tool that we can use to be able to implement and explore, as well as deploy machine learning models and algorithms. Machine learning models are programs that we train on data, and then we use those programs to make predictions. So we might want to maybe create a machine learning model that predicts house prices based on a historical data set or data set that we already have that has data in relation to, say, something like area of the houses that we have, number of bathrooms, number of floors, the number of bedrooms, number of kitchens, etc. So if we have a data set that comprises of that information, as well as the corresponding house prices, we can train a machine learning model, which is just a computer program that will understand the different patterns within that data set and then be able to make newer predictions once we give it new houses. So instead of being able to undertake a manual task that we would end up undertaking of looking into historical data and coming up with a realistic prediction, we can use these machine learning models which we would train on historical data that would give us fairly accurate predictions about what we want. So in our case, let's say for an example of a machine learning problem that we might, a machine learning task that we could end up doing, it would be that we would end up maybe predicting house prices, create a machine learning model that we use to predict house prices based on maybe factors like area, number of bedrooms, etc. We might also end up creating a machine learning model that would end up classifying or predicting whether an email that contains some content is spam or not based on generally its content. On the other hand, we might end up creating a machine learning model that groups customers' data based on their purchasing behavior. So a machine learning model will just look at data and then it decides to group that data. So, you could create a machine learning model to make predictions. It's important to take note that when we are creating a machine learning model, we would normally use what are called algorithms, which would be complex mathematical functions that we can use to create machine learning models. And these functions or mathematical functions, they work differently. There are ones which are more like black boxes, which are quite complex. They're not easily explainable, but again, you can still explain them if you sit down and extensively try to understand various concepts. There are machine learning models which are based basically on just probability. Others are based on calculus concepts. Others are based on vectors. So they all work differently. So what would happen is that when you're creating a machine learning model, you would use an algorithm, which is that complex mathematical function, to train, to create that model, then take the model and train it on data. The process of training a machine learning model, normally we refer to that process as supervised learning. So when we say that we want to train a model on historical data, we would refer to what is called supervised learning. But when we don't want to train a model, we just want it to make predictions based on just the data that it has seen, and be able to perform a task like grouping, then in such a situation, we would perform what is called unsupervised learning. So those are the basic concepts that we are going to be talking about. And R is a programming language, just like other programming languages that we can use, and it contains what are called packages, which are just chunks of code that have been written by other experts to make your work easier. So instead of writing, say, a package to apply machine learning, to create machine learning models, there are already existing packages that we can use to be able to perform that task. And there are also other packages that help perform other related tasks, such as there are packages that you can use to perform data visualization, to explore the data set before you ensure that it's in the right format for training. So a package like ggplot is a package, that's the data visualization R package. There's a package such as there's dplyr or dplyr, which is a package that we can use to perform data analysis or create summary tables that later we would use ggplot to create visualizations on. So R is an ecosystem that contains so many packages that we can use as data scientists, data analysts, or data professionals. One more concept to take note is that when it comes to machine learning, I've already highlighted this, but it's important to highlight it again. When it comes to machine learning, we normally would classify machine learning to a supervised learning or unsupervised learning or reinforcement learning. In some other cases, another category can be created. It's called semi-supervised learning. So they usually, but majorly, people tend to classify machine learning into 3 buckets. Supervised learning, where you have regression and classification, and also you have clustering, which is, and you have supervised learning and unsupervised learning. In supervised learning, you have regression and classification. So you would train data and then use that data, and then train a model, and then use that model to make predictions. And in unsupervised learning, you have clustering as one of the techniques. There's also dimensionality reduction. It's market basket analysis or associative learning. There's a whole lot which we do not necessarily cover in this workshop. Like even anomaly detection is part of unsupervised learning. So that's also important to take note of that before going a bit more deeper. One more concept to introduce before we now go into the next step of why we would want to learn about these concepts. When it comes to supervised learning, we have regression and classification, which are like sub topics. In regression, we create a machine learning model and use and train it to make predictions afterwards. But in regression, we predict a numerical nature. So we mean numerical variable. So we train a model to be able to make a numeric or continuous to make a prediction for a continuous variable or numerical variable. On the other hand, for classification, we would create a model so that it can make a prediction for a categorical variable. So that's where regression and classification differ, where you have these models, but they predict variables of a different nature. So you can think of classify, which is just to classify something into buckets. It's just what is classification and regression. And when we come to talk about the models, the type of models or the type of models that we are going to be talking about, you'll hear of the terms regressor, and also you'll hear of the term classifier. Those are just models. We just call them just they're just other words that we can use to call models. So let's just quickly talk about why machine learning would be important in R, and why we would want to use R for machine learning. You can implement machine learning concepts in various languages, even a tool like PHP, which is a web development language, even in JavaScript. There are even already libraries for that in those languages if you don't want to use other specialized tools like Python or R. But the reason why you would want to use R is because maybe you have your entire project based in R. Maybe you did reports already in R. And R has a vast ecosystem of packages, including for machine learning tasks. And then you just use those packages for that. And they would still apply the same concept, because the machine learning concepts that you're going to be learning, like working with a particular algorithm, which one would be maybe something like a decision tree algorithm, the concept is the same all across. The only thing that's different is just its implementation in how it's done in one language over the other. But again, if you look a bit more deeper, there's usually a question of performance. But in many cases, people don't go for one particular language initially for the reason of performance. It's usually just to be able to ensure that you help business stakeholders answer some questions, some critical questions, or you help reduce costs in an organization. And if a model that you've developed in R helps address that problem, then that's still okay. So Generally, R has numerous or thousands of packages, especially also, and a few of them have been designed for machine learning tasks. There are libraries like Caret, there's a library called Random Forest, there's Keras, there's XGBoost. These are packages. In R, we term libraries as packages. So these are packages that we can use to implement machine learning models, so to create machine learning models. R also offers exceptional data visualization capabilities. If you want to explore and understand the patterns within the training data set, before later cleaning and using the training data set for the training of a model, then you can use state-of-the-art data visualization packages such as ggplot 2. R also has a strong community of active users, and that means generally there's a whole lot of documentation when it comes to problems that arise pertaining to machine learning. If you come across a solution or a problem that you're not sure what error you're getting, you could always head on to you just head on to platforms, online platforms, where you could get support like Stack Overflow. Even when you ask a tool or an LLM or large language model like ChatGPT, it's highly likely that the LLM has been trained on existing R documentation and other articles pertaining to even the problem that you might be facing. So it's highly likely that you're going to be able to find a solution in a short period of time, as opposed to implementing these tasks in other languages. Maybe a language like Rust, you're on your own. Maybe if a few people within that community are not available at that particular point in time. When would you want to perform machine learning with R? I think when you want to maybe understand how when you want to get a deep understanding of maybe statistical properties of your data set, you might want to use R even for performing statistical tasks in order to uncover maybe patterns before now creating machine learning models. When you want to also try to understand also sometimes you might want to I think a good use case would be maybe develop maybe new algorithms or conduct experiments quickly. So if you want to do that in a record time and you're really conversant with R, then that would be a tool that you can quickly explore and see what you can get out of the tool itself. There are various reasons. These are just a few of the reasons that one might want to use R, because R provides all those tools. So in terms of types of machine learning, I've already talked about supervised learning. This just involves that category of machine learning where you would train your model. In unsupervised learning, you would not train your model. In reinforcement learning, you would have an agent which would learn by interacting with an environment, and it would learn by trial and error. So it would receive feedback in the form of what are called rewards and penalties. In supervised learning, when you're training a data set, you would normally have in that data set, we usually call it, in that data set, you can call it a training data set, we would normally have what is called we have feature set as well as a target. Features are independent variables, and the target is usually the dependent variable. So our goal would be to train your model on a subset of the historical data set. Assuming you had a historical data set with 100 records, you would split that data set into two. A bigger chunk or proportion, like 80%, would have a training set. So you would use your model and train it. You take your model and train it on the 80% of the data, so that it learns that for the corresponding independent variables, these are the values for the dependent variable, for the target variable. And then once you have trained it on that data set, you would then use it to make predictions for 20% of the independent variables, and it would give you the potential target values or dependent variable values, and then you compare those values with the original values that were there to just see how your model performed. And there are various evaluation metrics that we can use. For classification, you can use accuracy, there's precision, F1 score, quite a number of them. For regression, there's R squared, there's also root mean squared, error. So there are, quite a large number, but those that I've mentioned are the ones that normally people would use. That's what we're going to see in terms of the implementation. So at this particular point, I am going to ask you to, I think one more thing I haven't explained. In supervised learning, we have a data set that has, a historical data set that has independent and dependent variables. We normally call that kind of a data set, labeled data set. But in unsupervised learning, we don't have a dependent variable. We just give it like independent variables, and that data set, we would call it, that doesn't have dependent variable, we'd call it unlabeled data set. So the goal is to have maybe a model to perform a task like uncover or cluster the independent variables into just different categories, which technically would be what you would want. All right, at this particular point, we're now going to moving into our practice work. I'm going to ask you to visit the resources link that we've shared in the description of this video. If I'm too fast, also feel free to pause the video, rewind, and you can always just catch up. So yeah, so that's, just click on that link and it should take you to the Afterwork website, and you can download the sample. You can click on the sample practice resource, and it should take you to a page that looks like what you're going to see here. Or is it just a second? Just a second. Didn't share that. So it should take you to a page that looks like this, and you can download the file itself. Sample workbook, actually, sample workbook. Just download the sample workbook. If you're an Afterwork member, you always have access to all the resources that you need. You can click on Practice Notebook, which once you've logged in, when you visit the link, you should be able to get to. And then the Solution Notebook. Just download both the sample, both the Practice Workbook and the Solution Workbook for Afterwork members. But if you're just here for curiosity, we just want to see what machine learning has to do, what happens with machine learning, just click on the sample workbook. Once you have done that, the next thing that we are going to do is to visit posit.cloud. So let me reshare my screen again. There's this platform, posit.cloud. You need to create a free account. That's what we're going to be using for working with R. So generally, we'll get to have a web-based version of RStudio and be able to use it for our analysis or for creating models, machine learning models. If you want to use your local version of RStudio, it's okay, but we highly recommend you use just this first for learning, and then you can work on your personal projects using now the local version. The reason is because our focus for now is just to learn how to work with the mentioned concepts that we had highlighted earlier: regression, classification, and clustering. We're not really focusing on troubleshooting, which sometimes people might be able to get or to come across, like issues, errors when working with packages. So click on that. You can pause the video, by the way. Create an account, a free account. So Posit is the company behind RStudio, and they also provide a web-based version of RStudio, but it has some limitation. But for now, we can use it for just learning. All right, once you've done that, the next thing that we need to do, so I'm going to shift to posit.cloud. So once you have already created an account and logged into your dashboard, you should get to this page. This is your dashboard. You can, sometimes you might see on the far left that you have, maybe this is on, so you can just click on this icon or just this hamburger icon to minimize, and you can also always minimize the top part so that you have the entire page to yourself. Then click on the far right, new project, then click on new RStudio project. And a new RStudio instance will just take a few seconds to deploy and open. So as that happens, you can also create a name, give your project a name. So you'll see at the top, if I minimize this, at the very top, I can give it a name. Seems I would need to log in. Let me do that quickly. All right, so you should have logged in. So at the very top, you can give it your project name. So this project would want to call it maybe Machine Learning with R, and press enter, and just wait for it to just load. You may not necessarily get login successful. Yeah, to just take you directly to the instance. So just waiting, depending on the speed of your internet, it might take a few seconds. All right, so it's loaded up. So the next thing that we need to do is to upload the project files, the workbooks. So to do that, once you've downloaded them to your computer on the files directory section, so you just click on upload, then upload individually. So you can do that quickly. I'll do that for all the files. I'll do that for the practice. I'll do that also for the solution, but for many of us should just have the sample practice. But for the AppTalk members, that's practice workbook. I think I can add sample. Where's sample? Sample. All right, awesome. Do that, then we can continue. Feel free to pause the video as well. Once you're done, the next thing that we need to do is just click on what you imported. So sample, it should open a text editor, and we have it in source mode. We want to first of all install the packages that are required. I'll click on install for it to install, which you will get to see here. Aside from that, what we also want to do is to visualize our workbook or notebook. It's an R Markdown file in visual mode. So I'll click on visual, and that should also load up, but I should get also a prompt. You can wait for a few seconds for the process to continue taking place, like the installation of our packages, etc. So this is the prompt. Let me say I'll use visual mode. That's what I want. I can minimize this. I can also make this a bit bigger so that it's easier to see. And now I can get started. So before I get started, I would need to have these ones first of all finished. But I can just explain a few things. We have some notes of what we have covered so far. Machine learning with R, supervised learning. I actually use a sample practice notebook because it's similar to what we have already. I'll just click on the sample practice, the practice workbook instead. I'll use the workbook, the practice workbook instead. I think, see. Okay, let me just use a sample. But for those who are working with the practice, it's just the same. It's only that you have more challenges in the practice workbook. All right, so starting off, we have supervised and unsupervised learning. We'll now get to go through supervised learning, the algorithms that we would interact with. So let's first of all, Caret, we'll import Caret. We've already installed Caret, which all the packages, I think it was one of them. So we can still rerun the same, doesn't matter, by clicking on here. You just even this a bit. We set it to quiet to true so that we don't get an output that may not necessarily help us. It just makes it a bit, doesn't look appealing. Then we can load the package. The Caret package allows us to work with just different machine learning algorithms that we can use now for creation of models. So once we've done that, let's now read the CSV from the URL, this CSV that we have. This is a CSV, and we are going to use it to train our data, to train our model. So once we have done that, let's prepare it. We are going to remove the missing values, and then we are going to also ensure that the data, the columns are also pre-processed. So for example, we would want to represent the SKUs with an equivalent numerical representation, the same case with education, as well as job role. And we would do that using the functions that you see here. So for example, we would convert the columns maybe to appropriate data types like experience. We would, to numeric. Salary, it's already you can convert it to numeric, but for SKUs, we'd convert it. We would convert it to a numeric format using as factor. The same case with education, a job role, etc. If you're not sure what's happening, we are referencing the column names by simply saying data, then using a pound score and experience, and we are storing the output of this operation to replace. We are replacing the column names with now what is happening on the right hand side. You can have a look at our workshops, specifically on maybe prior R concepts like data wrangling, data analysis. We cover a whole lot of that, so you can have a look at them in our chat, in our YouTube channel, or even our platform. You should be able to get those courses there, and they should help you to just go through acquiring that skill. So once you've done that, we should be good in terms of having our data sets ready. The reason why we would do this is because machine learning models, when we are training them, they need numerical data. They would not take textual data. There's only one type of machine learning model that I know that takes categorical data, or data as it is in terms of a categorical format, and that would be CatBoost. And we're not using CatBoost, the machine learning algorithm. It's usually an advanced one, but for our case, we're just going to use the basic machine learning models. Here we remove the name column because it may not be of importance. We don't want to train our model to just use the name as a factor during its prediction. Then we set seed for reproducibility. The idea here is to ensure that when we want to take our historical data set and split it into a training and a test set, so a training set would have, we would use the training set to train the model. So the training set would have the same records. We want to ensure that it has the same records every time when we are running this code, and we would need to ensure that our seed is set at 123. If you change it to another number, the other person needs to ensure that they use the other number that you have here. But for consistency, we can use 123. Just an integer would do. And then we create, use this create data partition function to be able to define our training set. And then once we have done that, once we have gotten our training data set from the data column, we would then decide to create the train data set as well as the test data set. So let's run this as well. So here we just splitting the data into training and test sets, and we want 70% of the original data set to contain the training data set and 30% to be test set. So that's why we say 0.7. 0.8 would mean 80%. Now the first type of regression algorithm, because here we are working with regression algorithms, here we are just talking about prerequisites. The prerequisites that we have here are just to ensure that our data is in the right format for training. So we are going to just work with now different algorithms and create different models, but now specifically for regression. And this is where we are predicting a variable that's of a continuous nature. So to work with the first type of algorithm, we would use the LM. So we are going to work with linear regression, which is a type of algorithm that establishes a linear relationship between the predictors, that's the independent variables, and the continuous target variables. And the idea behind this algorithm, how it works, is that it creates some sort of line in between the points to minimize the difference between the predicted and the actual values. When would we want to use linear regression? Most importantly, when we have a data set. Once we have a training data set, if we have a training data set that has lots of numerical variables that are highly correlated with the target, then linear regression is usually the best type of model to use. However, linear regression has many assumptions. Aside from that, you need to check for what is called multicollinearity, which means you need to ensure that you don't have in your independent variables that are highly correlated with each other. So you need to drop one or so, or leave the other. So, and also you need to also take into consideration of normality of those independent variables, whether each and every independent variable follows a numerical distribution. So we use, to create a linear regression model based off linear regression algorithm, we use the LM function, and we pass to it salary and this particular character dot to specify that we want to use all other variables in the data set that we have in data, that's in the data, which is the trained data set that we specify here. We want to use all the other variables in this trained data set aside from the salary variable. We want to train that model and to take into account of that as the feature set, and then use the salary column as now the target variable. Here we just specify the training data set that we want. So let's run this. Once we are done, we then make predictions on the test set. So test set, we had already created it here. So we're going to make predictions for the target values so that the model can, it's going to make its own predictions. Then we'll compare those predictions with now the original values for the target variable for test set. So which we do here, we run this to make prediction for the test sets, and once we do that, we use, by the way, the predict function to do that. Once we do that, once we have done that, made the predictions, we then calculate the root mean square error, and the root mean square error would generally be the square root of the average of the squared differences between the actual salary values in the data set and the predicted values. And our interpretation would be that we would want a root mean square error value that's closer to 0, and usually less than 10% of the target variable. So for a target variable, the average of the target variable could be salary. It might be maybe 60,000. That might be the average. I'm just saying so, but you need to do your calculation before that. There are functions that would allow you to do that. So once you figured out that's the average, that's the mean, then you need to ensure that the root mean square is less than that. Let's say less than 60,000. So our root mean square in this case would be 7,000. So actually, less than 10% of the average. So the interpretation would be, once you get the average here, you need to have 10%. Less than 10%, this would be still 6,000. So you need to have maybe one that has, for linear regression, less than 6,000. But it's okay if you look at that. But again, you could always create other models and then compare their root mean square errors and see which one is much more closer to 0. Aside from that, this is just a first run through or the first creation of the first version of the model that we've created, we haven't yet optimized our data set. We haven't added the data that we might want from external data sources that we would think would be important in our training data set. And also maybe our data set might not have many records. Like you can see it's 6 times 7. So we have 6 rows in this case, but we can decide to we can decide to add more data and work with that. So, but generally that's linear regression. So let's see how we can create a decision tree model for regression, and we call them regressors. So we have created here a linear regressor, regressor, you can call it a linear regression regressor or decision tree regressor, the same case support vector regressor. So we're going to create those models for each. So for decision trees, we don't use the caret package. We would normally use the rpat package. So we're going to import it, and then we follow almost a similar process. So instead here we're using rpat instead of using lm. So here we're using rpat. We specify our feature and our target variables, and then we make our prediction and then calculate the root mean square error. Here we have 8026 root mean square error. So it means that a linear regression actually performs better than decision trees, which is okay. All right, let's do the same thing now for also create a model, a support vector machine model. So by the way, decision trees regressor normally works by dividing or creating what are subsets of data based off the feature set that we have, so the independent variables. So it creates more like a tree, so like a decision tree, but like a tree, but the subsets for each and every branch is usually as a result of the relationships that it uncovers from the feature set. The decision tree normally works really well when we have a data set that's nonlinear. If we have lots of categorical and non-categorical variables in our features, then it works really well. Or one more thing, for linear regression, if there are outliers, it also performs poorly. For decision tree, outliers are okay. Yeah. So we haven't even done again optimization, ensuring data is in the right format for decision trees. So we can just say this is okay. Support vector machines is another type of algorithm that we can use to create a machine learning model that makes a numerical prediction or continuous prediction, continuous variable prediction. So we import this package where we can be able to work with the support vector machine. And by the way, this type of algorithm uses vector concepts behind the scenes. So it takes historical data set or training data set and it plots them in a Cartesian plane. Then it finds a best fitting line that cuts across the different points, and that line is usually referred to as a hyperplane, and then you're able to make predictions out of that. So I won't go again deeper into that explanation. The idea is just to get you started, and we could look deeper into that if you want. We install the package for support vector machine. So okay, we would need to restart. Okay, we can restart R, doesn't matter, it's still okay. Let's see, it's telling us it needs to restart, but it's fine. No worries. Let's see, happens when we install. So we've installed it, and then we can now make predictions, and we make predictions. So we get 8200 for decision tree. We had 80,000, 8,000, and for linear regression we had 7,000. So still linear regression performs best. For support vector machines, they normally work best when you have smaller data sets, but again when you also have a larger number of variables. So if you have, usually say data sets with a higher number of variables to the records would be data sets that can be termed as to have high dimensions. So that's something to note. But again, that's something also to note. Random forests is another type of algorithm that we can use to create a regressor, or that model that we use to make a continuous prediction. Let me just I don't know whether. Okay, so I just wanted to yes, I think this works better. So random forest would be an advanced type of algorithm that uses multiple decision trees. So random forest works more like decision trees, only that it uses multiple decision trees. Rather than just use one decision tree, it takes the results of multiple decision trees and then does an average of the outcome of each individual decision tree, and we are able to predict accuracy. And the idea is that you're able to reduce the error that the decision trees do provide. This type of algorithm also is suitable for those data sets that are suitable for decision trees, like ones that you have maybe many categorical and numerical variables in the feature set, in the independent variables. So let's do the same thing. So let's work with this. Let's import that random forest. We'll import random, then we check for regression. We would again still follow the same process, only that we are using a different function, making our predictions and then calculating the roots mean square error. And here we got some information about the package, but we're really interested in this. So we have, this is actually better than even linear regression, 6,677. So it's much more closer to 0, and we can use this. The only problem with random forest is that if there are cases where we would need to interpret how a model arrives at a prediction, then this may not be the best type of model, because it uses multiple decision trees, and interpreting that might be a bit more difficult. So you might opt to use a different model and optimize a different model. Lastly, we'll get to learn about another advanced type of model or algorithm. We can classify this type, gradient boosting machine, which is what we are going to learn, and random forest, as what are called ensemble learning algorithms, or ensemble algorithms, just ensemble methods or ensemble techniques. And ensemble, as the word says, just together. Those types of algorithms tend to use multiple weak algorithms, and by the fact that they're using multiple individual algorithms all together, they're able to ensure that they minimize the errors of those particular algorithms. So technically, aside from just using, say, a collection of the base ones are the ones that we have learned support vector, regression, and decision tree, and linear. There's also another one that we haven't covered called k-nearest neighbors, or KNN. Aside from those, ones are called base models or base algorithms. We can create base models from them. What these ensemble learning or ensemble algorithms do is that they use multiple of those, and then they apply strategies for just reducing the errors that would result from just using them individually. So GBM uses it enhances the accuracy of multiple weak learners. So if you have, let's say, multiple, if you want to use, say, something like GBM, just know that you are using multiple algorithms. The only disadvantage is that you might also, actually there are a few disadvantages. There's one on computational resources. You tend to consume more in terms of resources because you're using more algorithms when it comes to training. And also interpretability. Sometimes having a complex model is usually difficult to interpret. So Yeah, so let's implement it. We'll install the GBM package for that, and then we install it, import it, and then use it and calculate its root mean square error. And voila, we get 4,384 from, linear regression. And just note that we haven't even, gotten more data that could potentially improve our model. Or even we haven't considered setting other hyperparameters, like defining which hyperparameters, which are just more like parameters. Like GBM here would have, these are just two different, like data is a parameter. So there actually are more, not could. There are actually more parameters for GBM that we might end up setting. Like you can see the ones that are here. There's formula, there is Bernoulli, there's distribution, there's weights, there are a whole lot. And we might, right now we're using just the basic, the default values for those parameters. If we wanted, we could further continue making them better. So we could use optimal hyperparameters and make our root mean square error even smaller. All right, so that's regression, where we are predicting one particular continuous or continuous variable. Let's see about classification. Classification, we are predicting a continuous variable. And some of these models are actually the same, only that we will introduce just one that's different. So classification, we are going to create our data. So what we want to do is to predict job satisfaction, whether it will be 1 or 0, which is just a categorical variable. So want to have a model, we train it off this data set, and we want it to make predictions for new records which have the independent variables, but they wanted to predict job satisfaction. So this is our data set. So we prepare it. And then once we prepare it, we remove that named column. We create our train and test set. We need to, so here I need to return here and import caret. The reason, by the way, if you get that error that you do not have that function, it means maybe your instance at some point stopped, so you did not have the access to this function. So we've imported again. We've imported caret again, because this function comes from caret to split the historical data sets to a train and a test data set. We want 80% to be train, test to be 20. Then we create now our first classification model called logistic regression. We use GLM to create it, and we have to specify that we are going to be creating to be predicting a binary outcome. Sometimes you might be predicting a continuous categorical variable that has only two, which is binary. It means when it has two values, either yes or no, 1, 0, that's a binary outcome. But if you have more, then you need to define this as something else. Multinomial, or is it a multinomial? Not sure, I'll have to look that up. Data train, here, train, you specify the train data set and you predict, you make predictions, and then you create what is called a confusion matrix, which would give us also not only the accuracy score, so here we also printing out just various metrics for evaluation metrics, but our focus for now would be on this particular accuracy metric, which would mean that 83% of the records that out of 10 records, it predicts 8 records correctly. That's 86. Sometimes the metric of success in a project can be just we need a model that can predict at least 80% of our records correctly. 1 is okay. And we have a confusion matrix that we can see here. There's a whole lot that happens with this. I'm looking at time. We don't have much time, but you can also use a confusion matrix to be able to evaluate the performance of your model. And we've provided a few notes over here, but you could always look at that. But for now, just note that accuracy is the most important well, it's not really most important, but we're using this as a basic one. But accuracy may not be the best in some cases where you have a training data set that is not balanced. So for example, if we had, like here we have more of ones than of zeros, so it's highly likely that in this data set the model will tend to learn more from the ones and zeros than zeros. But yeah, and there are strategies to go about balancing that. So that's logistic regression. You can think of accuracy of 0.8, but we would normally want it to be higher, 0.9 or so, 0.95. Support vector, let's reload this. Predict and also check for 83. It's almost the same. And also random forest, let's see. Still okay. Okay, well, let's not import it. If you import it, we'll reinstall again. Let's yes, so let's create that. Random forest has an accuracy of 75, but again, you'd also need to check on the confusion matrix. But yeah, those are just strategies. Now we've created models for classification as well as regression. There are many models still, even for classification. We only covered 3 that you can create. So on unsupervised learning, where we do not train our algorithms or our models on specific data, we're going to cover clustering. Clustering just involves being able to group a data set into just have to be in groups. So we could be able to use this technique to group similar data points together based on just patterns in the data set. So let's import these libraries that will allow us to perform clustering. So we load our data set, and then we can just select the specific columns that we want. Still, this is just part of data processing. And then these are and we also have decided to scale, like we want our data set to have a particular scale. We don't want some values to influence, which are big, to influence how the prediction is done by the model. And then we perform k-means clustering. We want to cluster our data into 3 categories. We define that. With k-means, you would specify 3 categories too, but you can always determine the number of optimal clusters or number of centers, optimal number of centers using the elbow method, which we do here. So let's load this. We have been able to cluster each record to each of these clusters, and we've defined a cluster that it belongs to. We can visualize the clusters in a plot using ggplot. Won't go so much into what we have here. You can go over through that. See, also you have gone maybe through ggplot, our data visualization with R. Then we check for the elbow method to see how many cluster points we would want. And here we can see the elbow is at around 2, so we can use 2 and change that previously in here where we have defined centers. All right, that's the elbow method. We have our clusters and where they belong to, and we can always get those records that we want. There's another type of clustering, supervised learning, that's called principal component analysis, and that involves generally, let me even just load the data set as well. It just involves being able to represent the data that we have into smaller number of variables called components. Like we have 10 variables, assuming we have how many? You have 6 variables. What if we wanted to represent these ones into just 3 different variables? Those variables would be components. They really wouldn't have any sort of numerical meaning, and we can do that through just this method, principal component analysis. We reduce them and preview them as shown. So we decided to create 4 components here, and that's it. And we can use this for training also. So that's it. If you are an Afterwork member, you can use the practice notebook. There are various challenges. I wasn't saying that you pause because this notebook, the sample one, doesn't have the challenges, but for the practice notebook, it has challenges, as you will be able to see. Like after each and every concept, you'll see a challenge. All right, the next thing, just get to think about how maybe to learn specifically maybe regression analysis with R or classification analysis with R. And that's it. All the best in your learning journey. If you loved this learning experience, be sure to give this video a thumbs up. And if you'd want to be informed when we post such